Welcome back to our ongoing look at polar coordinates. Right, last time we figured out what they were and how to plot them. Right, r comma theta, a circle of radius r, rotation angle theta. Alternatively, a line segment of length r rotated by theta. Either or is fine by me, really. And that's what we did last time. Well, what we need to do now is not just make them, not just plot them, but also go from rectangular coordinates to polar coordinates, and from polar coordinates back to rectangular. So let's jump right in. The first bit's actually pretty easy. If you have something in polar coordinates, r comma theta, then getting it back in rectangular is pretty straightforward, right? We have seen this formula before. If you're out here at, say, r cosine theta, r sine theta, then there it is, x comma y, right? I already covered this, right? Triangle inscribed in our circle. The hypotenuse is r, the angle here is theta, or, the equivalent angle is theta. And so that will put us at cosine is this length over r, so this length is r cosine theta. Similarly, the height of this triangle is r sine theta. So yeah, that's the easy way. That's done. We can take care of that just like that. But let's do it the other way. Let's suppose I'm at some point, and that point isn't given to me as a polar coordinate, right? I do not know the polar coordinates. I just know x comma y. How do I get r and theta that would make this same point? And that's a little harder to answer. Because, well, what's r? What's theta? There's no equation that solves for it directly. But hey, isn't this a right triangle? And this is r right here. So if I know x and I know y, then r, via the Pythagorean theorem, right, r squared is x squared plus y squared. So hey, we got it. And then theta, right, this angle of rotation, well, the tangent of that is y over x. Right, I could also use this cosine of theta or the sine of theta, but that would bring in r, and I don't know r. I only know x and y, so I would have to use tangent here. And that's what we got. We have two major equations now. R squared is x squared plus y squared, and tangent of theta is y over x. So you might say, oh, okay, well, we'll just take the square root of both sides, get root x squared plus y squared, and then we'll take the arctangent of theta, or arctangent of tangent theta, giving us arctangent of y over x. So there we go. That's our polar coordinate. Well, not really, right? Remembering that this will always be positive, which is nice because I like positive radii. The negative we could technically also have with a plus or minus situation here, but you can always take the positive one. That's fine. But you would have to compensate for that. And that's because arctangent only gives you values in two quadrants, right? It only gives you values in the first quadrant and in the fourth quadrant. So if you were out here at some x comma y, and you took the arctangent of that, it would actually tell you, oh, theta is negative something or another. It would actually try and spit you out in the fourth quadrant. And that is because arctangent only gives you values in quadrant 1 and 4. So you would have to compensate for that. It is not always going to be the case that you can just take the arctangent and know for sure where you are. You have to be a little smart about it. You have to recognize, okay, I'm in quadrant 3, arctangent gave me this value, so my actual angle theta is this guy. That's what you would have to do. And that's really all you have to do. So if you were to convert some points here, say I've got 6, 8, and -4, -3 in rectangular coordinates, then I wanted to find the polar coordinates. Well, this r is the root of the sum of the squares, right? So r is 10, and arctangent of 8 over 6 is 53.13 degrees, give or take. And since we're in the first quadrant, arctangent will give us exactly what we need. We don't have any other alterations that we would have to make. Now, is this the only value for our polar coordinate? Of course not, right? I could have -10 for my radius, right, if I took the negative root, and this would then be 53.13 plus 180, or 233.13 degrees. That's fine. That's fine too. Of course, you can add 360 or subtract 360 degrees to either of those as many times as you like, and you also still have polar coordinates that generate this same point, right? They all point to 6, 8 in rectangular coordinates. They all point to A. So here's the question. Is B going to be calculated doing the exact same thing, right? The square root of negative 4 squared plus negative 3 squared is square root of 16 plus 9 squared of 25. So r is 5, and the arc tangent of negative 3 over negative 4 is 73.61 degrees. Is that going to be what B is? No. No, of course it's not. And that is because this point, 5, 73.61 degrees, would spit you out in the first quadrant, right? 73 degrees is between 0 and 90. It's between 0 and 2 pi over 2 radians. So it's going to give you something in the first quadrant. Positive radius gives you something in the first quadrant, but we all know negative 4, negative 3 in rectangular is somewhere in the third quadrant. This is not an appropriate value. Now, technically speaking, negative 5, 73.61 would probably handle it, but just be smart about it. Be smart. Think about what you have, think about where you are, and apply the appropriate transformations. That's what you have to do when you're making these new points. Alright, well, enough about points. Enough about points. That's been fun. We're good on that. We're done here. We can also use these same equations, these same equivalent values from polar and rectangular, to convert equations as well. Right, suppose I wanted to convert the equation x minus 1 quantity squared plus y squared all equal to 1. I wanted to turn that from rectangular points to polar points. Well, x is r cosine theta, right? Y is r sine theta. So we're just going to stick all that in there. And now after I square everything out, I've got r squared cosine squared theta minus 2r cosine theta plus 1, right? That's coming from squaring out this guy right here. And then r sine theta squared is just r squared sine squared theta. The r squared sine squared theta and the r squared cosine squared theta just becomes r squared. And so what I'm eventually left with, after I move things around a bit, is r squared is 2r cosine theta. Divide both sides by r. I can do that because r is never 0. I guess technically it could be, but that would be awfully trivial, right? A circle with radius 0 is just a point. So this would be totally valid. R equals 2 cosine theta is an equivalent way of producing all the solutions to this equation, right? All the x, y values that satisfy this equation have polar coordinates r, theta that satisfy this equation. And curiously enough, this equation might be easier to solve. You just put in some values for theta, see what r has to be. Now, what if you wanted to actually graph this thing? What if you wanted to graph that? Well, you could just do a whole bunch of guessing, right? Without converting anyway, although you could convert and just put in a whole bunch of values for theta. You could also just fall back here, put a whole bunch of values in for x, and see what y would have to be to satisfy the equation, right? This is something you probably did in pre-calculus algebra from the very, very outset, right? X has to be something, so what's y got to be? If x is a half, then I have plus or minus root 3 over 2. See what would happen if x is 1, if x is 2, if x is 3 halves, if x is 3/4, if that'll work. That sort of thing. Just do all those values and get a whole bunch of points on the XY rectangular coordinate system, and plot all those and see if you have enough idea of how this thing looks. That would work, right? That might take a lot of point plotting, but that would work. Another option. You could recognize, oh yeah, from my extensive background in conic sections, I know this is a circle of radius 1 centered at 1, 0. And you wouldn't be wrong. That is totally legit. But I'm imagining most of us don't actually have a commanding knowledge of conic sections. So let's not assume we have that. And definitely let's not do that in this class. If you want to look it up, it's actually in the textbook, and it's actually kind of interesting, but we got better time. We got better things to do with our time. So the final option here, which we'll be looking at in our next video, is recognizing I have r equals something in theta. That looks a lot like y equals something in x, right? We have a independent variable theta and a dependent variable r. Could I not treat that equation, r equals 2 cosine theta, as a function of r in theta? And yes, we can. In the next video, we will start looking at functions in polar coordinates. Right? So we don't have to just do what we've done here. We don't have to just convert equations. We can actually convert functions. Or better yet, we can take something that's not a function. Right? This is not a function. This fails the vertical line test super hard, as you would see. Right? It fails just based on this point alone. But this is actually a function in polar coordinates. So yeah, we are going to have a whole bunch of polar functions that we can look at in the next video. I'll see you then.